Hello again. I hope you're doing well. Let us maybe finish chapter 4 this time. Okay, so let's get started. Do chapter 4, and we're doing. So, what we want to do, we're going to talk about Newton's method and antiderivative. So, Newton's method is a way to approximate the roots of equations. So for example, if you look at these two functions here, this one and this one, if you set them equal to 0, there is no formulas that we can use to find the roots of this or the roots of this one. And when that happens, we approximate the roots. And one of the ways to approximate the roots, I know you know what the roots are. Roots are basically values that you substitute for x and makes the left side 0. Same is here. So these two equations, we don't have any formulas to find the roots, so we have to approximate them. Newton's method is a way to do that. Okay, so the way it works is this right here. So what we do basically, let's say we have a function that has a root. Let's say over here has a root, and what we do, we start with some number here. Let's say this one right here. This is our guess. So we start with x sub 0, and then we go to the function, and at x sub 0, we're going to draw a tangent line, right? And then we see where the tangent line intersects the x-axis. That would be our second guess, x1. And then we go to the function again from that point, and then we draw a tangent line again, right? And again, the tangent line hits the x-axis here. That would be our x2, and so forth. I'm going to explain that in a second. Okay, so that's the idea. So we make an initial estimate that is close to the root that we're looking for, and then we're going to determine the next estimate by using that estimate. Now, where does this formula come from? We're going to talk about. And do as many iterations as you like, until you have the accuracy that you desire. And the accuracy is basically the difference between the last two that you find. Let's say you do it 10 times. So this is x sub 9 and x sub 10. And then the difference between these two, absolute value, you want it to be smaller than, let's say, I don't know, 0.001 or something, 3 decimal places. And then you stop once you have that. Okay, so let's see where the formula comes from, and then explain the process here. So let's say this is the root. Let's say this is the root that we're looking for. And for that root, we are going to find a initial root that is close to it. So let's say this is the root here we're looking for. So we go to a point right here, x sub 0. So we go to the function, draw the tangent line at that point, right? And then see where it crosses the x-axis. Then from that point, again, we go to the function and draw another tangent line and see where it crosses. And then at that point, we go up, draw another tangent line, and so forth, until we get close enough and with the desired accuracy. Right? All right, so where does the formula come from? But the formula really is easy to understand, because what we start with is just the number x sub 0. And then we draw the tangent line. So we write the equation of the tangent line at x sub 0. How do we do that? Well, that would be f of y minus f of x sub 0 equals to f prime at x sub 0 times x minus x sub 0, right? So if you solve for y here, you get y equals to f of x sub 0 right, plus f prime of x sub 0 times x minus x sub 0. Now, what we want to do, so that's the equation of that tangent line, right? So we want to find its x-intercept. To find the x-intercept, we have to set y equal to 0, right? And that's what I did here, see? So we said y equal to 0, and then solve for x. Now, the x that we're going to find is going to be x sub 1, right? So first we start with x sub 0, the next one would be x sub 1. And x sub 1 is basically the first x-intercept of the first tangent line, right? Right here. So we call it x1. I called it x1 already. So we solve for x1. We isolate it on one side and we end up with this formula. That's where it comes from. Now obviously if you start with x, if you take this x1 and put it back in here and find another one, we call the next one x2, right? And so forth. So that's how we find it. There's just a formula for it. So we don't have to go through all this process again, right? We have a formula. So x sub 0, of course, the first one when n is 1, it would be x sub 1. So x sub 1 is going to be x sub 0 minus f of x sub 0 over f prime of x sub 0. And then x2 is going to be what? x1 minus f of, again, x1, right, over f prime of x1, and so forth. Okay, so that's how we apply the Newton's method. So here's an example. We have f of x equals to x to the third minus 3x plus 1. And the interval we're looking for, root 4, is this interval. The reason we know there is a root here is because if you take 1 and substitute it here, you get what? You get 1 plus 1 is 2 minus 3 is negative 1. And if you substitute 2, that's 8. 9 minus 6 is 3. So we know this function is below x-axis at 1 and is above at 2. So it has to have a root between 1 and 2, right? All right, so since we know it has a root at between 1 and 2, we're going to start with a point that we are given, which is 2. So we start with 2. We are given that. Okay, so we substitute 2. We find f prime, f we have. So that's f prime. So we start with x sub 0 equal to 2, right? So it would be 2 minus what? So x1 would be what? X sub 0 minus f of x sub 0 over f prime of x sub 0. So x1 would be 2 minus f of 2, just substitute 2 in here, over f prime of 2, substitute 2 in here. So you substitute 2 in there, we get 3, substitute 2 in there, we get 12 minus 3, 9. So 2 minus 3 ninths, which is about that, right? And now we substitute this, right? So x2 would be this number minus f of this number over f prime of this number, right? Now notice that is a lot of arithmetic. So what we can do is use a calculator to do that, or a computer to do that iteration. So this is 5 iterations, right? And we got 1.53. That's the root, right? So we're looking for this root right here, between 1 and 2, right? There are other roots here, we don't want those, we want this one. Okay, so how do we do this with a calculator? So what we can do is, let me just quickly show you. So we are going to put the f of x and f prime of x in y1. So that's x to the third power minus 3x plus 1, and f prime is 3x squared minus 3. 3x squared minus 3. Okay, now we're going to go to home screen, and then here's what we do. We start with let's see. So we start with 2, right? 2 minus, so we're going to put parentheses. Now remember, we put f in y1, so we go get y1 under variables, y variables, and function, and y1. y1 of 2, right? And then divided by, again, y2 of 2. y2, again, we get it from same place. So that's y2 of 2, right? And then close the parentheses there. And so that's right. Now, once we get this number, we're going to use all the decimal places. So we're going to store it. See, store is right there. So we're going to store it in. Oops. Let me get the answer one more time. So I'm going to store it right here. You see, store in the letter A. So letter A is right here. Alpha A. There. And press enter. Right? So now I just use with, I'm going to use A. Right? So I'm going to do the same thing here. I'm going to bring the entry, second entry back. So all I have to do is just change that to what? Change it to A. So I'm going to put A, and then again A, and A. There, that's my second number. Now I'm going to store it in B, right? I can store it in B and do it again. In fact, I can even store it in A because I used A already. I can store it in A again. So let me store it in A. Store in A. Okay. Now A has this new number, right? Then I'm going to get the entry back, the one with A in it, that one. Press enter again. Well, I get a different one, right? And then I do the same thing. I store it in, in A. You can use a different letter if you like, but I use A. So I'm going to have what? Another number. And so I get closer. You see, so let me show you. I did it here with different letter. Instead of A, I use B, so you can tell how many times we did it. And notice that we did 1, right, 2, 3, 4, 5 iteration, and we got 1.5320, so, right? So that's the approximation we got. Okay, that's the idea. It's not really that hard. It's very easy to use, and it's programmed into computers, and we can use computers to do this. Now, typically Newton's method is used to find roots fairly quickly. However, things can go wrong. So what can go wrong? Well, first of all, you know the formula already have, right? What if f prime is 0 at one of these points? If f prime is 0, then we're not going to get the next point. That's it. We're stuck in that one. We can't move on, right? So basically it gets stuck. So for example, right here, if you start with x sub 0 here, right, and you're looking for a root, what happens is you get this and you hit this. And then at this point, when you draw the tangent, well, this never crosses the x-axis. And you get nothing out of this formula, right? So it gets stuck. It's possible to get stuck like this. On your way, the tangent line at one of those points, one of your estimates, is horizontal, and then you're stuck. Or it's possible that you're looking, let's say, for this root, and then you get this root, which you didn't want, right? You start with this, and then, so you draw a tangent, and you see you hit over here. Now, if you go over here and draw a tangent, you're going to get close to this root, not the one you actually want it. And that's another problem. That happens if your initial value is too far away from the roots that you were supposed to find, right? Okay. And so the approximations may fail to approach a root entirely. Here is an example of a function, an initial guess. So here we go. What happens is, in this case, let's say we start with this initial guess, and the root, is over here. And notice that at this point, we hit 1, and then we go tangent at 1, we hit 0. And we go tangent over here, we hit 1. So we're going back and forth between 0 and 1. We never reach the root, right? It's possible. Of course, if you pick a different initial point, that may not happen, right? So it's possible to get stuck this way. Fluctuates between two values. All right, and let me show you one more iterative process, and that is, it's very important, in fact, in pure mathematics and also in many application problems. We're not going to get into it in this course, but I wanted to just mention it, that there is a iterative process where we have a function and there is an input. So you take the output and make it input again, and then you get the output, make it input again, and then you go through this cycle. Now when you do that, you end up with numbers over here. So you start with some x sub 0, and then you get to an x1, and then an x1, right? So you put the x sub 1 back in here, you get x sub 2. You put the x sub 2 back here, you get x sub 3, and so forth, right? And if you continue this way, in some functions, these numbers actually approach some fixed number, fixed value. They all approach that. And in some other functions, they don't approach any number. So there's an interesting concept here. Is used in many applications of mathematics. Let me show you an example. So here's a function, 1/2 x plus 4. So it's this line right here, right? That line right there. So this is the function 1/2 x plus 4. So let's say we start with x equals x sub 0 equal to 0, right? So we go to the function, we go to 0. The function value, when you substitute 0, is 4, right? So you substitute 0 here, you get 4. Now we're going to make 4 an input, is output. Now we're going to make it an input. How do I make it an input? Well, the easiest way graphically is to draw y equals to x. Any point on this line, x and a y are equal, right? So when I get to this y value, if I go horizontally parallel to x-axis and hit this line, well, now my y value turns into a x value, and they're the same, right? But that would be my input. So this is the output. Now I'm going to make it the input. Then I go to the function, right? Now I have a y value here. This is my x2. And then I'm going to make it what? Make it an input. Then I go to the function. I get an output, then I make it an input. Then I go to the function and so forth. Now if you do that, notice that these fluctuations, they are approaching, these two are approaching some number, right? And that number turns out to be what? 8 in this case, okay? So that's another iterative process that you can just take the next number by substituting the previous number into the function, right? That's another way to do iterative process. All right, so that's all I have to say about this section. And the next section is about antiderivative. So let's talk about that, and we are done with chapter 4. Now there is a video here in the notes, you can click on it and watch it. It is by Richard Feynman. I'm sure you have heard of Richard Feynman. He's a very famous American physicist, and he was involved in Manhattan Project, and I believe heard that he got depressed after the use of the atomic bomb, and lived in Latin America for a few years, came back to the United States. But he's a great physicist, and he has 2 volumes of physics textbook that is free online. You can search for Richard Feynman's textbooks and you find them. But here he compares mathematics and physics. It's an interesting little video here. You should watch it. So I'm going to move on and talk about antiderivative. So the need for antiderivatives, of course, arises in many situations when you have, in fact, in nature, we are given derivatives already. When you observe a phenomena, for example, if you drop something from some height, right? Let's say you drop something from some height. So what you observe is actually derivative. So you can say how fast this thing is falling. You can have some numbers, right? The time and then the distance it falls, right? If you collect that, that is actually rate. So we are having rate here. So in nature, what we collect is actually rate. So what we have to do in order to find the patterns, well, the patterns are the functions whose rates we observe in nature. So we need this antiderivative. So antiderivative is, if I say, what's the derivative, what function has derivative of 2x? Well, you can do it in your head and say, well, I know that's x squared, right? So we say 2x squared is antiderivative of 2x. But it could also be x squared plus 1, or x squared plus any constant, right? So that's the general antiderivative of 2x. Why? Because if you take the derivative of this, you get 2x. So the function whose derivative is 2x is this family of functions, x squared plus c. That's the idea of antiderivative. So let's talk about it. So we showed that given a position function, we can take the derivative of it and find the velocity, and then we can take the derivative of the velocity and find acceleration, right? So now we are given, suppose we are given acceleration, right? So we're given acceleration, we want to find what? We want to find velocity. Suppose we are given velocity, we're going to find what? The position function. So the process of going this way, we have spent almost 4 chapters on, and that is taking derivative, right? We go from left to right. And antiderivative is to go from right to left. So if we are given these functions, can we assume that these are rates? This is a rate of a function we don't know and find it. Can we assume this is a rate of a function and find that function? Well, that's what we want to do here. We want to start it here and then continue in chapter 5, right? All right, so think of antiderivative as the inverse of derivative. So x squared is the derivative machine, right? You put x squared here, 2x comes out. Now, antiderivative machine, if you put 2x in it, x squared comes out, right? So infinite number of, we're going to talk about that. This antiderivative is indefinite, but for now, let's talk about infinite number of different functions that can have the same derivative, right? So x squared plus 1, x squared plus 3, x squared plus c, they all have the same derivative, right? In fact, derivative has to do with the shape of the function, right? So if 2 functions are actually the same shape, where we just move them up and down, right? Then the derivative at any given point doesn't change, you see? At this point, the slope of the tangent would be exactly the same, right? So that constant doesn't really do anything in terms of derivative, because derivative of a constant is 0. Okay, so it's a family of functions whose derivative is what? 2x. All right, so a function f, capital F, is an antiderivative of the function f. If you take derivative of it, then you get f for all x in the domain of f, right? So when I say x squared is x squared plus 3 antiderivative of, let's say, 2x, yes, if I take the derivative of this, what do I get? I get 2x, right? So that means x squared, you can call it capital F of x, for f of x, let's say plus 3, for f of x equals to 2x, right? So that's the idea of antiderivative. And we can easily find these things, right? So I talked about all this. You can stop the video and read this. But so are there any other antiderivatives of f of x? When we find one of them, you know, x squared, are there any more? Yes. In fact, there are infinite number of functions whose derivative is 2x. X squared plus any constant. And now another question I want to answer is this. Are there any others that are not of the form x squared plus c? No. Remember from the corollary second one to the mean value theorem, we said that if two functions have the same derivative, if f prime equals to g prime, then f has to be g plus some constant, right? So if this is the if the derivative of this and derivative of some other function, right, are the same, then the difference between them is a constant, right? That's what this says. So that means in this case, we cannot have any other answers to this question that has different form than this form. It's going to be the same form, x squared plus some constant. And there are infinite number of them, of course. Okay, so if we have two antiderivative functions, let's say we say, okay, f is antiderivative and g is antiderivative too. Well, in order for them to have the same derivative, the derivatives have to be equal to. And if the derivatives of the equal, then one of them has to be the other one plus some constant, or the other way around. You write g equals to f plus c, right? So if we have any other answers, they're all going to be of this form. Okay, so general form of an antiderivative, and we talked about that already. You can stop the video and read it, but I'm going to do an example. All right, so for the following function, find all antiderivatives. Okay, well, antiderivative of x to the, what's the antiderivative of this? Well, so derivative of x to the third is 3x squared, so x to the third is actually antiderivative. And then we know the general antiderivative would be if we add what? A constant to it. So this function is the general antiderivative of what? Of 3x squared. So we can go backwards, okay? So with derivative, we say derivative of x to the nth power is nx to n minus 1. Now, the antiderivative of x to the n, we're going to have a notation for it, which looks like a elongated s, and that's the integral symbol. So that means antiderivative of x to the n, and the variable of integration, we put it here as dx. Just like when we take the derivative, we put dy dx, right? So you can put the dx here. This was added later when calculus was invented. This was added later to indicate that we are dealing with what? With the variable x. Okay, so the formula is x to n plus 1 divided by n plus 1. Okay, so that's the formula to find antiderivative, and then plus what? plus some constant for power functions. That's the formula. Okay, for other functions, we go backwards in the table. So for example, we know the derivative of sine is what? Derivative of sine is cosine, right? So antiderivative of cosine, well, is sine. We go backwards in the table. Okay, so antiderivative of cosine is going to be sine and then plus c. That's the general answer, general antiderivative of cosine. So for the following function, find all antiderivatives. Well, for this function, it turns out that if you think about it, we know ln x, derivative of ln x is 1 over x, right? So that means antiderivative of 1 over x has to be ln x, right? Now we have to take into account whether x is positive or negative, because you know the domain of ln cannot be negative. So for positive x-axis, it cannot be 0 either, right? So positive x-axis, for positive x's, x values, the derivative is 1 over x, and antiderivative is 1 over x, right? Now, for negative x values, then we have to make this minus x, right? Because if x is negative, this can be negative, so we put a negative here. So what is the derivative of ln of something is 1 over something times the derivative of inside, which is negative 1. And that would be the same thing. So whether x is positive or negative, the derivative will still be the same, 1 over x, right? So what we have to do is we say the derivative of ln of absolute value of x is 1 over x, right? So to make sure that the domain of ln is positive, we put absolute value here. So when we say, what is the antiderivative of 1 over x dx? We say is ln of absolute value of x plus c, right? All right. Again, you can stop the video and make sure you got this under control. But we're going to get to formulas very soon. So given a function, the indefinite integral of f is denoted by this. So this is elongated kind of s is indefinite integral, right, of f of x. Indefinite integral of f of x dx. And the answer to this would be the antiderivative function plus some c, because we always have this c here because the derivative of c is 0. So no matter what you put here, you get the same derivative. So we always have to put this c. So the expression f of x is here is called the integrand, right? Integrand. And the symbol, of course, is the indefinite integral, this symbol right here. And the variable x is the variable of integration. So that is variable of integration. Okay? And I talked about this already, that the reason you can think of the shape of the function, and derivative is nothing, has to do with the shape of the function. So if the shape of the function does not change and it just goes up and down, all the x values here, you see at all of those points, the derivative is basically the same, right? So that means all of these have the same derivative, which is 2x. So antiderivative of 2x dx is x squared plus c. Another way to read this is antiderivative of 2x dx if you want, but this is called actually officially indefinite integral. Okay, so let's call it that. Or you could just call it integral or indefinite integral. Okay, don't say antiderivative, it's not official. Antiderivative is actually this, right? All right, so the integral or indefinite integral. And we talked about this already. So the dx indicates that the antiderivative is taken with respect to x. The constant c has derivative of 0 is called the constant of integration. And so indefinite, that's how you read it, indefinite integral of f of x, right? And the integrand is the stuff inside here. Okay, so power rule for indefinite integral. Power rule, I just talked about that. So if you have if you take derivative of this, you're going to end up with x to n. So that means what? Antiderivative of this is x to n plus 1 over n plus 1 plus c, right? Is the inverse of differentiation. In differentiation, what do? If you have m, you take what? You take m x to m minus 1, right? So you have to, here you subtract, here you add 1. And here you multiply, but here you divide, right? What do we do first here? We subtract 1 from the exponent and then multiply, right? Here we add 1 and then divide, right? All right, so n is not negative 1, obviously, because if n is negative 1, what happens? Well, the denominator becomes 0. So this formula doesn't work when x is to the negative 1 power, which is 1 over x. But we already talked about that. We took care of that case, right? That case is that case is ln absolute value of x plus c, right? So n equals to negative 1, we don't use this formula, we use this right here. Okay, let's use it on this one. So what's the indefinite integral of x to the 5th power dx? Well, it's x to 5 plus 1 over 5 plus 1 plus c, which is 1 over 6 times x to 6 plus c, right? That's all. Here's the table, so we go backwards basically. So differentiation formula for a constant, derivative of constant is 0, right? So the antiderivative of a constant here, we assume what? We assume that x is to the 0th power here, right? So when we have a constant, we have to think of it this way. Antiderivative of k x to the 0th power dx. So what's the formula? Take 0, add 1 to it, so we get 1, right? And then divide it by 1. And then k is there, right? So k, we keep it. We can bring it out in the outside of the indefinite integral symbol. So we get kx plus c, right? So antiderivative of a constant is kx plus c. And when you take the derivative of this, you get the k, right? X to n, we already talked about. For antiderivative of 1 over x is ln x absolute value of x plus c. E to the x is 0, is itself, right? Because the derivative of e to the x is e to the x, so antiderivative of e to the x is e to the x, right? So indefinite integral of e to x dx is e to x plus c. And derivative of sine is cosine, so antiderivative of the indefinite integral of cosine is sine plus c. Now, the derivative of cosine is negative sine, so antiderivative of sine is not cosine, because you see, if you want to go backwards, you have to have negative sine x, right? This is cosine, but we don't have negative sine x here, so we can put a negative here. I'll put a negative here. That doesn't change anything because negative times negative is positive. But it changes the form of it, so we can say the answer is negative, whatever this answer is, which is cosine. So it's negative cosine plus c. Okay, so when things that we have here don't match what we have in the table, we can modify it a little bit. And we're going to do some more in chapter 5 on this. But for now, that's good enough. And all the other in the table, we can go backwards, like antiderivative. I keep saying antiderivative. Indefinite integral of secant squared x dx is tangent, because the derivative of tangent is secant squared. antiderivative, okay, I keep saying, so I'm going to say it. Antiderivative of cosecant is going to be what? Well, we know derivative of cosecant is what? Is that, right? So that means antiderivative of cosecant cotangent negative has to be cosecant. So that's not what we have in the table here, right? We have the minus is missing here. So what do we do? Well, we are going to put a minus here, right? I'll put a minus here. Now this right here, we know the antiderivative of that, and I have to erase that. So we put a minus here, a minus here. So the antiderivative of this, we know is what? Is cosecant. So it's the negative of whatever this is, so it's negative cosecant plus c. Derivative of secant is secant tangent, so antiderivative of secant tangent is secant. Derivative of cotangent is negative cosecant squared, so the antiderivative of cosecant squared is, well, let's see, we have to put a negative here again and a negative here. And it would be negative or whatever this is, which is cotangent, right? So negative cotangent plus c. Now we know the derivative of sine inverse is 1 over square root of 1 minus x squared. So antiderivative of 1 over square root of 1 minus x squared, and the dx is missing here, and I'll put it there, is sine inverse x plus c, right? And the same is true for tangent inverse. We know derivative of tangent inverse is 1 over 1 plus x squared. So antiderivative of 1 over 1 plus x squared is tangent inverse plus c. And it's the same thing for secant inverse. So the antiderivative of 1 over x times square root of x squared minus 1 dx is secant inverse absolute value of x plus c. Okay. So again, we're going to talk much more about this in chapter 5, but that's antiderivative. So verify that each statement is correct by showing that f prime equals to f of x. Okay, so here is what the answer is. Is this answer correct? Well, if this answer is correct, then derivative of it has to be what? Has to be that. So we just take the derivative in A. So we're going to take the derivative of this. Derivative of x squared over 2 would be x, right? So it's 2 times x squared over 2, which is x. Derivative of e2x is d2x. Derivative of c is 0. So what do we get? We get what we have here, so it's correct, right? So now, what about the b part? The same thing. We take the derivative of that. You know, when you take the derivative, you see this is what? This is a product rule, right? So derivative of this would be derivative of x times e to x plus derivative of e to x times x. Then minus derivative of e to x plus derivative of c. And well, these two get cancelled, so we get x e to x. So it's correct. Okay? Now let f and g be antiderivatives of f and g, capital F and g, and let k be any real number. So now it's similar to the laws of limits when we talked about limits, right? So the indefinite integral of a sum is basically the sum of antiderivatives, right? So we can actually, if we have sum or difference, we can separate it into what? Into two. So this is actually integral of f of x dx plus or minus integral of what? G of x dx. And the answer to this is this, the answer to that is that, and then plus c. There is actually a plus c1 here and plus c2 here. We can combine it into one c, right? Constant multiples. If you have a constant multiplied by a function here, you can put it out, right? So this is the same as k and then integral of f of x dx, right? And the answer to this is capital F of x times k plus c. So from this theorem, we can evaluate any integral involving a sum, difference, or constant multiple of functions with antiderivatives that are known in the table. Evaluating integrals involving products and quotients or compositions is more complicated. We're going to look at those in Calculus 2, actually, the second volume of this OpenStax calculus, right? So integral of f plus g, f minus g, integral of some k times f, we can do. But integrals of like f times g or f over g, those are a little bit more involved, and we're going to need more rules. So we're going to leave those for Calculus 2. So let's do some examples here. This one is easy because they're just a bunch of what? There are a bunch of power functions, so we can do them separately and separated, right? So here we go. This is a. Do you agree? What's the antiderivative of 5x to the third? So we keep the 5, and then we take x to 3 plus 1, and then divide it by 3 plus 1, which is going to be what? Which is going to be x to the fourth, and then 5 over 4, right? That's the first part. The second part is going to be the antiderivative of this. Again, we keep the 7, negative 7. Then, so we keep the negative 7. That would be x to, keep the negative 7 would be x to 2 plus 1, then divided by 2 plus 1. Right, so that's 3, and that's 3, so we get this one. And then this one, 3x, we keep the 3 plus 3. And then would be x to the power of 1 plus 1 over 1 plus 1, right? So that's 3 over 2 and x to the second plus this 4. We keep the 4. Now you remember we assume that there is an x to the 0th here. So it would be x to 1 over 1. So that's 4x right here plus c. So that's the a part, right? So not very difficult. Now the second one is a little bit more involved because we have to what? We have to separate these and divide by this common denominator because we don't know how to do quotient yet, right? So we do x squared over x and then this over x. X squared over x is just x. And x to the, what's that cube root? Cube root is actually x to 1/3 divided by x to the first. Just x, that is x to 1/3 minus 1, which is x to negative 2/3, right? And then we keep the 4 outside. So what is the antiderivative of this? It would be x to, there's a 1 here, right? The power is 1. So 1 plus 1 divided by 1 plus 1, 2, 1/2 x to the second. Keep the 4 here, it would be what? Would be x to negative 2/3 plus 1 divided by negative 2/3 plus 1 plus c. Now negative 2/3 plus 1 is just 1/3, right? It's just 1/3. And this is 1/3. 1 over 1/3 is 3, and 3 times 4 is 12. And it would be x to 1/3 plus c. That's the answer for B part. Again, make sure to stop the video and make sure you follow what I just did. Now the C part, what do we do with this? Well, it looks like the table, except it has this extra 4 here, so we could bring it out. And then 1 over 1 plus x squared, we know what this is. That's just tangent inverse, right? We know the derivative of tangent inverse is that. So this is 4. And the antiderivative here, all of this, is just tangent inverse plus c, right? Again, going backwards in the table, right? All right. D part, tangent x cosine x, we can write it as, write tangent as sine over cosine times cosine. The cosine goes away. So this is just what? Just that. And we know the answer to that is negative cosine plus c. Why? Because we know the derivative of what? The derivative of cosine is negative sine, right? So we know antiderivative of negative sign is going to be cosine, right? But we don't have negative sign, so we put a negative here and put a negative here again. Same trick, right? And we get the answer. So the answer is cosine plus c, right? And I explained here why we did that. You can stop the video and watch and look at it. Okay, so we're going to talk about basics of differential equations. Differential equations actually is two courses you can take. One is ordinary differential equations, and one is partial differential equations. And if you're getting into maybe electrical engineering and some other engineering, you need both. So what is a differential equation? Well, a differential equation is similar to equations you have to solve. You have solved before. For example, if I have 2x minus 1 equals to 5, well, you can solve this and the answer is what? X equals to what? 3, right? So this equation has a solution, and a solution is a number, right? That is an equation that you're familiar with. Now, a differential equation involves derivatives. So for example, if I say y prime equals to 2x, now what I'm looking for here, I'm looking for a function whose derivative is 2x. That is a differential equation. There are many different types of equations, differential equations. Differential equations that involve only the first derivative, they're called first order. If they involve the second derivative, that means the largest derivative that involved is second derivative, like this one. Then that's the second order, third order, and so forth. There are other categories that within these that you're going to talk about in Calculus 2 a little bit more, and then in differential equation course. Here we just want to solve some basic differential equations, okay? So these are differential equations, but we are not going to solve these differential equations here, right? Not even this one. But we're going to solve simple ones like this one, okay? So let's do that. All right, so verify that the function is a solution to this differential equation. Now, this we can do. That means we are given the solution. We just want to check to see if this is a solution for this equation. Now remember, for differential equations, the solutions are not numbers but are functions, right? So this is a differential equation. So the solution for this could be a bunch of functions. It could be more than one. But for now, we are given one solution. Is this a solution for this? If this function is a solution, then its derivative, right, plus 3 times itself has to equal to 6x plus 11. If that's the case, then we say yes. So let's do that. So we're going to take this, all right, and we're going to take the derivative of it, right, put it here. That's y prime. Derivative of e to negative 3x is e to negative 3x times negative 3, right? Derivative of 2x is 2. So that's y prime plus 3 times the function itself. Is it equal to 6x plus 11? Let's see. Yes. Right? Do the algebra and you see that, do the operations and you see that's the case. So we say that this differential equation, this function is a solution for that differential equation, right? In fact, in many applications, that's where all the formulas come from, like in physics and in engineering. We start off with some differential equation, right? And then you get the rest of it. For example, in physics, F equals to ma is a differential equation, because a here is what? Is a second derivative of what? Of position. So F equals to ma is a second order differential equation. And all the Newtonian physics formulas come from this differential equation. In fact, at MIT, there is a professor, and it's an open course, you can take a physics course, and you see that he derives every Newtonian physics formula from that, F equals to ma. Starts from one corner of the board, and then the other corner comes up, he comes up with all kinds of formulas from that differential equation. You solve it. Okay, so let's look at another one. Find all solutions of this differential equation. Now, one way to solve differential equation is to separate the variables, right? So we're going to write it as dy dx instead of y prime. Then we separate the dy and the dx. So what we're going to write this as dy equals to 2x dx, like this. Then we are going to consider a 1 here and take the indefinite integral of both sides, like this, right? So indefinite integral of 1 x to the 0 is just, y to the 0, because the variable of integration here is y, but the variable of integration here is what? X. So the answer to this would be 1 y to the first power over 1, we don't write it, equals to x squared plus c, right? So y equals to x squared plus c, right? That's it. So the general solution is the family of solution to this differential equation. In this example, we are free to choose any number we wish. For example, 0, right? We can pick any number for c, right? That's the general solution. So this is called, if we pick a number for c, then, for example, let's say y equals to x squared plus 3 is a particular solution for that differential equation. But this one right here is the general solution, right? All right. So it says find a particular solution to differential equation y prime equals to 2x passing through the point 2, 7. So let's see. Well, first, what do? We write it as dy dx. I just did this for you, right? Integrate both sides. And then on this side, you just get y plus c1, right? Because this is an integral, you can put a c1 there. But usually we keep the c's and then we wait for all the c's and put them at the end as one c, right? We don't put a c here and put a c here and then bring them, and we just forget about this c, just concentrate on the c on the right. So this would be just y equals to x squared plus c, right? So c2 minus c1 is just some other constant, which is, we call it c, right? So that's the general solution. Now, we want the solution that goes through this one, right? Now, what is that solution? Well, that solution would be when x is 2, y has to be 7. So we're going to substitute 7 here, and then 2 for x, and see what c is, right? And it looks like c is what? 3. So this is a particular solution passing through this point, right? All right. A differential equation together with one or more initial values is called an initial value problem. So if we have a differential equation and we are given an initial value of that function, then we have an initial value problem. For example, here. Give examples of initial values needed to solve this. Possible initial values would be, now notice that this is a second order differential equations. So when we do this, we're going to have to find a constant for that. We're going to find a constant for that, right? In order to find y, we're going to have two constants. One would be, for example, what is the initial value of y? Let's say at 0 is 2. And what's the initial value of y prime? At 0 is 3, right? So if you have a second order differential equations, you need two initial values, right? And again, I don't want to get into it that much because this is a whole course, and also we're going to talk more about it in Cal 2. But let's look at some examples. Verify that this function is a solution to the initial value problem. So first we have to make sure that this, right, works for this formula. And then we have to make sure that y of 0 is 3. Now this we can check right now. If we put a 0 for t here, what do we get? We get 2 times e to 0, which is 2, plus 1, so that's 3. So that's check. Now we have to take the derivative and make sure the derivative actually works. The first derivative plus 2 times itself has to be 3e to t. And we can check that easily, right? Take the derivative plus 2 times itself. Do we get 3e to t? Yes. Right? Again, we can stop the video and do what and take a look at this and make sure it makes sense. And we checked that already. This result verifies the initial value, therefore the given function satisfies the initial value problem. Velocity of a moving basketball. We use Newton's second law, which states that the force acting on an object is equal to its mass times its acceleration, right? We assume that the only force acting on a baseball is the force of gravity. So in this formula, we ignore the resistance of air, right? So force of gravity, what's force of gravity? Is the weight of the baseball, right? So weight of the baseball has to equal to what? ma, right? So you see this F here is a force of gravity, which is the weight of the baseball. And the weight of the baseball has to be equal to ma, right? But what is weight of an object? In physics, you know weight of an object is mg. And since this is the planet and the object is falling this way, then this vector is negative g, right? So m times g is the acceleration due to gravity, and mg is the weight of an object in SI unit, right? So that's the mg. So the force is negative mg. It's negative because it's towards the center of the planet, right? And the distance is getting smaller as an object falls, right? So negative mg, which is F, has to be equal to ma, and the m's go away. So negative g is a, so negative g is our velocity, or velocity prime, which is acceleration, right? So negative g is acceleration. So velocity prime equals to what? Negative g when something falls under the influence of gravity only, the force of gravity. So v prime is negative g. So how do we find v? We have to take the integral. So we take the integral of both sides. Integral of v prime is vt, and integral of negative g is what? Well, negative g is a constant, right? And the variable of integration is time, t. So integral of negative g would be negative g to the second. What am I doing? I meant t, not g. So let me erase all that. So here, we keep the negative g, and then we put t, right? Because this, we assume there is a t to the 0th power here, right? So it would be t to 1 over 1. So negative gt plus some c, right? But this c, what's the nature of this c? The nature of this c is velocity, because velocity equals to this. So instead of calling it c, we call it v sub 0, initial velocity, and we keep it as initial velocity. Okay, now, if we have v, how do we find the position function? So let me show you here. So if we have s of t, we get v of t if we take the derivative of it. And then if we have v of t, we get a of t if we take the derivative of it, right? We could also go this way, right? So from A of t, if you start from A of t, you can get V of t, and from V of t, we can get S of t. That's what we are doing right now. We did that previously. Now we're going to do that. So we're given basically A here. Think of this as A of t, right? We say, okay, if A of t is negative g, then how do we know this is A? Because of Newtonian, formula that we had, F equals to ma, and A is an acceleration in this formula. So A of t, which is V prime of t, equals to negative g, and from here we found V of t, which is this here. Now, how do we find S of t if we have V of t? We have to integrate it. So we have to integrate A of t to get V of t, and we have to integrate V of t to get S of t, right? And these are dt's here, right? Okay, so what is the integral of V of t? That's S of t, right? And integral of negative g t plus V sub 0. Integral of negative g here is negative g t to the second over 2. And then plus, there is a t to 0 power here again, right? Because it's a constant, so it would be V sub 0 t, right? And then plus some c. But what's the nature of this c? Is the position, so we call it S sub 0. So you probably have seen this formula from physics, and that's how you derive it from calculus, right? We started with what? F equals to ma, and we ended up with a formula that governs the movement of an object under the influence of the gravity on this planet close to the surface. All right, so that's the idea. Again, can you stop the video and do this yourself one more time? Make sure it makes sense. So I have it here, what we just did, right? So S of t is this formula. If we are given position, we can take the derivative and find velocity. If we are given velocity, we can take the derivative, find acceleration. And the other way around. If we are given acceleration, we can find velocity by integrating it. And if we are given velocity, we can find the position by integrating it, right? All right, so velocity of a moving baseball. A baseball is thrown upward from a height of 3 meters. So here's a height of 3 meters. A baseball is thrown upward, right? All right. So the height is 3 meters. With an initial velocity of V sub 0 is 10, right, meters per second. And the only force acting on it is gravity. The ball has a mass of 0.15 kilogram at Earth's surface. Find the velocity of the baseball at time t. What is the velocity after 2 seconds, right? Now, so V of t is going to be what? Is going to be negative 9.8, right? T. This is acceleration due to what? Due to gravity. In feet per second would be 32 feet per second, right? And in SI unit is 9.8 meter per second, right? That's acceleration due to gravity. That's our G, right? I'm not sure which one. I think you learned it this way or this way, whichever it is. I think it's this way, right? SI unit. SI units. Standard International SI units. Okay, so our G is 9.8 because it's planet Earth. Other planets have different G, right? So Vt is equals to, when you integrate that, so it's going to be that, right? V of t is negative 9.8 t plus V sub 0. And then we're going to, so that's the velocity. We found the velocity right here. So what's the velocity after 2 seconds, right? Now we need to know initial velocity. Well, initial velocity at t equal to 0 is given, is 10, right? We know v sub 0 equals to 10. So we just put 10 for v sub 0, and we have the velocity. Now after 2 seconds, what's the velocity? We put 2 there, 2 for t here, and we get negative 9.6 meters per second. So after 2 seconds, even though you throw it up, after 2 seconds it's coming actually back down because the velocity is negative. So it's coming back down after 2 seconds. It's going to go up and then come back down. After 2 seconds, it's on its way down, right? With a velocity of negative 9.6 meters per second. All right. So, decelerating car. A car is traveling at a rate of 88 feet per second, about 60 miles per hour. When the brakes are applied, the car begins decelerating at a constant rate of 15 feet per second squared. How many seconds elapse before the car stops? How far does the car travel during that time? Again, what we are given here is, well, a car is traveling at the rate of this 88 feet per second. So we're given velocity when the brakes are applied. The car begins decelerating as a constant rate of 15. So this is the acceleration, but of course, since is applied by the brakes, right? Let's say you have a car that is going this way, right? So the wheels are turning this way, right? If you apply the brake, the brakes actually apply a force in the other way. So the brakes are actually create a deceleration, right, in this direction, right? So it has to be negative. If you're going to the right is positive, going to the left is negative. All right, so we know the acceleration here is negative 15. So let's do this. So given velocity at time 0 is 60 when the brakes are applied. So v of 0 is basically that. Acceleration at time t is negative 15 when the brakes are applied. So a of 0 is that. And s of 0 is 0. So we assume at the moment that you brake is s0. So you want to know how much the car travels. So v of t is the integral of acceleration. So v of t would be integral of negative 15, which is negative 15t plus c, right? But remember, this is velocity, and this is the initial velocity, right? So that's just 88. We know that. So that's the velocity function, right? For the movement of this object. That's the velocity function. And so it says to find how long it takes for the car to stop, we need to find the time, t, such that velocity is 0. So if I set the velocity equal to 0, t equals to 88 over 15 seconds, right? And during that time that the car stops, how far does the car go? Well, let's see. Again, s of t is the integral of v of t. So s of t would be the integral of the velocity. And integral of velocity, how do we take the antiderivative of negative 15t? Would be negative 15t squared over 2. Antiderivative of 88 is 88t plus some constant. And that constant, since we are given that s of 0 is 0, right? So our constant is going to be just 0. So we are going to have this position function. Now remember how long it takes for the car to stop? That. During that time, how far does the car travel? Well, we're going to substitute this t for the t here. I use a calculator. And we get 258 feet. That means you got to be careful when you're driving around. When you see something, even if right away you press the brake, if you're going 60, was it 60 miles per hour? I believe so. Was it? Yes, 60 miles per hour. So if you're going 60 miles per hour, it takes you what? And if you push the brake right away after you see something, it's going to take you 258 feet before you can stop. 258 feet is a lot of distance, right? So you gotta be careful when you drive. Okay, you can stop this, go back and make sure you understood this problem. I'm gonna stop the video here and stop chapter 4. This is it. This was the end of chapter 4. So I'm gonna come back here and say bye to you. I think it was a little bit longer than I wanted it to be, but that's okay. We finished chapter 4. So take care, and I see you in the next video.